Today we will dive into the fascinating world of particle astrophysics, exploring one of the most complex yet exciting fields of modern science. In this journey, we will start from the Earth's core, move through subatomic particles, and venture into the farthest corners of the universe, in an attempt to understand the invisible mechanisms that govern matter, energy, and the fundamental forces ruling the entire cosmos. Particle astrophysics is an interdisciplinary field that combines elements of particle physics, astrophysics, and cosmology. This branch of science allows us to study subatomic particles, the most fundamental units of reality, and their role in the evolution of the universe itself. The allure of this discipline lies in its ability to connect the microscopic scales, such as those of fundamental particles, with the vast cosmic structures and processes that span billions of light years. To better explore this vast and fascinating field, here are 8 key points to deeply understand the mysteries and discoveries revolutionizing our understanding of the universe. 1. Particle physics. The foundation of the universe and its laws. Particle physics is the branch of physics that studies elementary particles and the fundamental forces they interact with. Elementary particles are the smallest units of matter and are divided into 2 main categories: fermions, which include particles like quarks and leptons, and bosons, the particles that mediate the fundamental forces. Quarks combine to form composite particles such as protons and neutrons, while leptons include particles like the electron and the neutrino. The fundamental forces governing the interaction between these particles are 4, gravitational force, which acts on all particles with mass; electromagnetic force, which acts on charged particles such as protons and electrons; strong nuclear force, which holds quarks together inside protons and neutrons; and weak nuclear force, responsible for some radioactive processes and nuclear fusion in the hearts of stars. These interactions are mediated by bosons: photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. Studying these particles and their interactions allows us to explore how the universe, from the microscopic to the macroscopic, is governed by universal laws. Discoveries in particle physics provide us with the keys to understanding the fundamental mechanisms that shape the structure of the universe and explain crucial processes such as nuclear fusion in the Sun or the exotic matter found in the cores of neutron stars. 2. Cosmology. The big picture of the universe. Cosmology is the study of the universe as a whole, focusing on its origin, evolution, large-scale structure, and ultimate fate. One of the fundamental concepts of modern cosmology is the Big Bang theory, which describes how the universe originated from a point of infinite density and temperature about 13.8 billion years ago. Since then, the universe has expanded and cooled, allowing galaxies, stars, planets, and ultimately life itself to form. Another pillar of cosmology is the idea of cosmic inflation, a period of rapid expansion believed to have occurred a fraction of a second after the Big Bang, explaining many of the observable properties of the universe, such as its large-scale homogeneity. The future of the universe is still uncertain and depends on various factors, including the amount of dark energy, the mysterious force that seems to accelerate the expansion of the cosmos. We may live in a universe that will expand forever or one that will eventually slow down and collapse on itself in what some scientists call the Big Crunch. 3. Particle astrophysics. Where the micro meets the macro. Particle astrophysics unites the fundamental laws of particle physics with phenomena observed on a cosmic scale, linking the subatomic world to the largest structures of the universe. A key example of this approach is the study of cosmic rays, high-energy particles that come from deep space and travel through the galaxy. These rays are mostly composed of protons but can also include electrons and atomic nuclei. They provide scientists with important information about the origin and nature of high-energy events, such as supernovae and black holes. Another area of research in particle astrophysics is the study of exotic particles produced in extreme environments, such as the centers of stars or black holes, which may help us unravel the mysteries of dark matter. This invisible matter makes up about 27% of the universe, but it neither emits nor absorbs light, making it extremely difficult to observe directly. However, its presence is revealed by the gravitational effects it exerts on visible objects like galaxies. 4. Dark matter and dark energy, the great invisible mysteries. One of the most fascinating and mysterious aspects of astrophysics is the presence of dark matter and dark energy. Although we cannot directly observe these components of the universe, we know they exist due to the effects they produce. Dark matter is a form of matter that does not interact with light or other forms of electromagnetic radiation, rendering it invisible. However, its presence has been inferred by observing the gravitational effect it exerts on galaxies and galaxy clusters. For example, the speed at which stars orbit around the center of a galaxy is much higher than expected if the galaxy contained only visible matter. Dark matter seems to act as a gravitational glue, holding galaxies and their large-scale structures together. Dark energy, which makes up about 68% of the universe's total energy, is even more mysterious. This form of energy appears to be responsible for the acceleration of the universe's expansion, a phenomenon observed with Type Ia supernovae. We do not know what dark energy is, but its discovery has radically changed our view of the cosmos, posing new challenges for theoretical physics. 5. Cosmic rays. Messengers from deep space. Cosmic rays are ultra-high energy particles traveling through space at nearly the speed of light. These particles come from mysterious and violent sources such as supernovae, supermassive black holes, and perhaps even events related to dark matter. Cosmic rays interact with Earth's atmosphere, generating a cascade of secondary particles that we can detect on the ground. By studying cosmic rays, scientists can gain crucial insights into high-energy events occurring in the universe. Moreover, cosmic rays allow us to explore phenomena that we cannot directly observe, such as the processes happening near black holes or in supernova explosions. Their origin remains largely a mystery, but ongoing studies of these particles may reveal much about some of the universe's most extreme phenomena. 6. Neutrinos, the ghost particles. Neutrinos are extremely elusive subatomic particles that interact very weakly with matter, so much so that millions of neutrinos pass through our bodies every second without us noticing. These particles are produced in enormous quantities inside stars during nuclear fusion reactions, as well as during catastrophic events like supernova explosions. Neutrinos are particularly fascinating because they offer us a unique window into the nuclear processes happening inside stars. Neutrinos can travel vast cosmic distances without being deflected or absorbed, making them excellent cosmic messengers. Neutrino detectors, such as the IceCube Observatory located under the ice in Antarctica, are helping physicists better understand these subatomic ghosts and their role in the cosmos. 7. Cosmic inflation, a primordial explosion. Cosmic inflation is a theory proposed to solve some problems with the standard Big Bang theory, such as the homogeneity of the universe and the absence of magnetic monopoles. According to this theory, in the very first moments of the universe's life, it underwent an extremely rapid exponential expansion, growing by an incredible factor in a very short time. Cosmic inflation not only explains some of the observed properties of the universe but also has profound implications for quantum theory. During this phase, tiny quantum fluctuations in the inflation field would have been amplified, becoming the seeds from which all cosmic structures, such as galaxies, galaxy clusters, and eventually planets and life, formed. 8. Dark matter, the great cosmic enigma. The last great frontier of particle physics and cosmology is dark matter. While we know it constitutes about 27% of the universe, its nature remains one of the greatest mysteries of modern science. Scientists hypothesize that it could be made up of yet unknown particles called WIMPs, weakly interacting massive particles, or perhaps consist of axions or other exotic particles. Experiments worldwide are attempting to reveal the existence of dark matter through various methods, but so far, none have provided concrete evidence. If and when we discover the nature of dark matter, the implications for physics will be immense, possibly requiring a complete revision of our current theories. In conclusion, particle astrophysics represents a field of research that is redefining our knowledge of the universe and its origins. It connects the microcosm of elementary particles and the macrocosm of astronomy, shedding new light on fundamental questions ranging from the origins of the universe to the nature of dark matter and dark energy. In this way, we are getting closer to a deeper understanding of the Standard Model and the fundamental forces that govern nature.